Matt Williams. I'm a consultant clinical oncologist at Imperial. And this is the next in our Horizons in Neuro-Oncology series. So the aim of Horizons in Neuro-Oncology is to try and help us find out and discuss innovations and research in neuro-oncology, but really with a focus for stuff that's relatively close to coming to the clinic. So I'm afraid there won't be anything mouse related in any of the HIN talks in the near future. So I'm delighted to welcome Raj Jena, who's a group leader at the University of Cambridge and also an honorary consultant clinical oncologist at Addenbrooke's. And he spent a long time with interest quite similar to mine, involving sort of brain tumours and computation, which is all I'm very excited about this talk. So he's going to talk to us, I think, about how you might be able to use synthetic DTI to predict radiotherapy toxicity, but I'll allow him to explain in more detail. Just as a reminder, we'll have about 40 minutes of talk, 15 minutes of questions at the end, and all of this will be recorded and go up on YouTube in a week or two's time once we've sorted it all out. Lovely. Raj, over to you.
Thanks, Matt. I'll just bring my slides up and just, if someone can holler just to check that you can see what I've got. So
yeah, I can see that.
Okay. So yeah, as Matt says, I was just thinking back, it's about 9 years ago, Matt invited me to one of the first computation and modeling meetings at Imperial, my first time coming to Imperial, in fact. And actually talked to Matt a little bit about some rudimentary thoughts around this bit of work. And it's interesting to look at 9 years, particularly with advances in machine learning and sort of deep learning and generative algorithms, how far we've come. And so I put this deliberately provocative title, but hopefully I'll explain why it says, am I faking it? Do I have your attention over the next 40 minutes or so? Let me wind my slides on. Okay, there's my boring disclosures. Everything I'm going to say is my own opinion and highly opinionated. So just briefly, what I'm going to talk about is the idea of an onco simulator, because I think if you're a mathematical modeler like Matt and myself, this will really be catnip to you. If you're not, I think it's an interesting idea to think about if you're interested in doing research that is close to the clinical data, because the principle of an onco simulator is that it's a model that starts with a patient's image as its initial conditions. Then I'll talk a little bit about the study that we've been running, collecting data for doing work with AI and models, and in particular, the neuro-oncology arm of that data. And then in order to analyze this data, we had a specific problem about missing data. And there we've solved it, we believe, using a particular type of generative machine learning approach. Okay, so what is an onco simulator? The word was coined by some Greek colleagues over 20 years ago, and it basically refers to the idea that you can create a very simple computational model that models some process that you're interested in, and you basically use a three-dimensional image as the initialization point. So this is an example of an onco simulator that I created many years ago, and it's using a technique called agent-based computing or cellular automata. You don't need to know any of that, but what we have is the initial scan of a patient who's had a glioblastoma removed, and in that scan, we have an area which is the tumor cavity. I've created a number of tumor nodes or agents with these crosses, and these agents have been programmed with some very simple rules, which is grow outwards from the tumor. How fast you grow depends on whether you're on gray or white matter. And if you head into a white matter bundle on your journey, then you lock onto that white matter bundle and you move along that bundle. So some very, very simple rules. And then basically the idea is that you can then sort of perturb that initial conditions of the model. And all I'm doing here is just pressing the play button and allowing those nodes to migrate through the brain. And you can see that now these nodes, instead of being in the tumor cavity, have engaged with different white matter fiber bundles in the area around the original site of the tumor. And then basically, if you do that about 1,000 times, and you then sum all of those trajectories over time, you end up with a probabilistic model of where these tumor cells might spread. Now, if you've ever done any radiotherapy planning for a glioblastoma, you would recognize this and you would think, yeah, when I draw on my clinical target volume for a tumor to encompass microscopic spread, this heat map is really sort of trying to inform what I'm doing when I draw my CTV. basically. And so the idea is that you can try and use a mathematical model like this to make some relatively simple but hopefully useful prediction of either a tumor response or a host response, which is what I'll come to. Okay, so can we use oncosimulators in radiotherapy? Modeling tumors are quite difficult because oncosimulators tend to use some kind of randomness underlying them to generate sort of different responses to different portions of your virtual tumor. And it's very hard to kind of map those out to the behavior of the real tumor in a patient. But we've used for years simple models to make useful predictions of effects on normal tissue in the brain, particularly with radiotherapy. And we know that these models generally are still helpful to bat an eye in the clinic even today. And so we have, from age-old data, these ideas that as you increase dose, depending on how much of the brain you're treating, the whole brain, 2/3 of the brain, or 1/3 of the brain, there's a certain probability that you may cause injury to the brain, in this case, over brain radionecrosis. And these calculations still underpin what we do clinically today. This is a VMAT, a particular type of radiotherapy plan that we're using to treat a relatively large tumor. So we end up with a fractional volume, about 1/3 of the brain. And how do we know it's safe? Well, we know from our experience and practice, but we also know basically because we can understand from these very simple phenomenological models that the risk of a patient, undergoing brain necrosis is going to be within an acceptable level compared to the risk of the patient dying of the tumor if you don't treat them with any radiation therapy. Okay, so the idea that we had is to take oncosimulators and maybe start combining them with the sort of machine learning tools that you use in data science. Because if you do any kind of integrative cancer medicine, you are typically trying to combine some data from image. If you're a radiotherapy specialist, that image includes dose data as well, because radiotherapy is a very spatially targeted treatment, and we can produce maps of where the dose goes. Perhaps some toxicity data, which is categoric in nature, maybe some outcome data that might be binary. So all these different sort of data sets kind of thing. And you then have to kind of work out, well, how do I build analytics pipelines to join all these things together? And then also, do I join all of these things together in one enormous machine learning model where all of the inputs come in at the same time, which is called early fusion of a machine learning model? Or do I join them in what's called a late fusing model, where what I do is I take each data set and try and simplify it with like a simple machine learning model, or perhaps an oncosimulator to generate some, slightly simpler output data. And that's called a late fusion model. So you sort of do little bits of machine learning in mini models, and then you feed them up to the mother of all models to make your final prediction, basically. And generally, we believe that late fusing models are probably better in the sense that they probably have higher accuracy levels. But more importantly, when you're talking to clinical colleagues, they're easier to understand, because if you can tell them what each bit does and what the model from each bit is doing, they're more likely to believe this mother of all models when it comes up with the final prediction about how the patient's going to do. So in order to build a model like this, a few years ago, we had the idea of how would you do this? And we realized that the only way to build a model like this was to try and collect the really good quality data up front. And so we had this idea to produce an AI study, and all it was doing was collecting really good imaging and outcome data for the specific purposes of building machine learning models that were particularly interested in time series data. So in other words, radiotherapy toxicity changes over time after you actually deliver the treatment. And so we created this study in partnership with Microsoft Research initially, called Hamlet-RT, that was designed to build toxicity prediction models in 4 tumor sites: prostate, head, neck, lung, and brain, which is what we're talking about today. So we capture the planning images, the diagnostic images in the case of brain with MRI, dose cubes, and cone beam CT images. And then we basically collect site-specific relevant patient-reported outcome measures at baseline, and then every 3 months for 2 years after radiotherapy. And the nice thing was we did this really cheaply because the whole thing was set up electronically on a very good data capture system that's used for clinical trials, basically. And so the overall study, we aim to recruit about 2,000 patients overall. This slide's already out of date. We're now up to 1,300 patients. recruiting at about 12 centres, including Imperial. And it's actually one of the top recruiting studies on the NIHR's radiotherapy study portfolio kind of thing. We've also, not for brain, sadly, but for one of the other sites, head and neck cancer, opened a parallel protocol in Calcutta, where we are looking to collect a different group of people. So even expand on the diversity that we already get from our 13 centres around the country. And the principle was we didn't have a specific endpoint to test. Well, not quite true. For two of the disease sites, we are looking to outperform some existing machine learning models for prediction using this particular approach. But what we wanted to do is basically build a really good data collection and federation system for those centres that are outside of GDPR. So that would be a really nice, good sort of shareable resources. So that if you come in the Hamlet RT as a centre, one of the bonuses is that you can run algorithms on all of the data. And I think what's been interesting about this is that from a machine learning perspective, I won't dwell too long on this because I realize this is a machine learning talk basically, but we've been able to build different levels of models. We've been able to build the simplest level models. Can we just draw around things in an image that we want to analyze? We've then been able to sort of build regression models that start to analyze features in our data set against some kind of toxicity sort of thing. The bit that we're looking forward to doing is building particularly sort of time series prediction models that are good at sort of taking data from different points in time and then trying to build a prediction based on the trajectory of something that has quite a complex change over time. And interestingly, maybe not be surprised to hear that the best time series machine learning data comes from Forex, so foreign exchange markets, and the people that do AI in that space trying to game the foreign exchange markets. So but the really interesting thing that we've got basically is the ability to now use some data synthesis models using generative techniques. And that's really what I'm going to focus on for this talk. So, okay, all right, I've actually talked about that already. So that's just this concept of which is better. Is it better to fuse data early and predict all into one model? Or is it better to kind of build individual machine learning models that start to work on each domain of data and then fuse their outputs of the machine learning model? And I've clearly declared where I stand on that front. So, okay. So coming back to brain, all right. So when we were thinking about what we wanted to analyze in brain, Matt and I sit there in clinic and we give patients immensely high quality radiotherapy. And Matt's patients never get brain necrosis from his radiotherapy treatment. Never, 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 ever. So it's almost like a never event. So in other words, we're basing our treatments and modifying what happens to individual patients based on an endpoint that we never see. So it is very hard to game that particular endpoint. But when our patients come back and see us 3-4 years later and we haven't given them radionecrosis, what they do, particularly when they're a clinical lecturer in epidemiology, is they say, my short-term memory doesn't work. I really struggle to switch between tasks. So if my phone goes off and I'm in the middle of writing something, it takes me 5 minutes to get back kind of thing. I can't hold attention. When I write a paper, I have to do it in 10-minute blocks and then go and do something else, physically, and then come back to it. And also, I just get such fatigue. If I try to use my brain for 8 hours a day, it's really hard. Now, these functions, I believe, are not related to how much brain we treat, and that basically this normal tissue complication probability is the wrong endpoint. But they are related to brain attention networks that govern the function of our brain. And basically, we have this default state, basically, a sort of daydreaming state called the default mode network, when we're not thinking about anyone in particular, we're not working on anything in particular. It's argued that some people believe that when men are in this default mode network, they are actually thinking about one thing in particular. I would beg to disagree. But anyway, it's our sort of neutral gear, right? And then a stimulus comes along that flicks you into some kind of attention task. So the first thing you need to do is to work out that you've got a stimulus that you need to respond to, and then work out what you're going to do about it. So a salience network, and then the executive network that says, oh, okay, I just heard the kettle boiling, I'm going to go and make my cup of tea, sort of thing. And we believe, or my hypothesis is that the functions of these networks are disrupted after we give radiotherapy, particularly after surgery. And we need to think about these networks as a chain, which is only as strong as its weakest link. So we need to work out the dose effect to every element of this functioning network in order to understand and correlate it between radiotherapy effects and toxicity. Just understanding what the dose to this part of the brain is not going to work, basically. So you can image these networks positions using functional MRI. You can either do task-based MRI, where you get people to do things in the MRI scanner, like, you know, sing a song or listen to some music or something like that, work out which parts of the brain light up. It's kind of like modern day phrenology, if you like. Or you can do what's called resting state functional MRI, where you simply take observations of the networks that are sitting there at rest, and then suddenly they flick to another state, and you image that and capture that. And if you can do enough observations of that, you can actually build up a picture of your networks without specifically having to perturb the patient. And it looks like in the functional MRI area, that particular approach is much more tractable, basically. So we have a large number of networks. Some of them are low-level functions like processing our vision or our hearing or speech. And then you come into these more interesting networks. So we decided that we wanted to build maps of these. And so we used a thing called the White Rest Atlas. It's a fantastic open source resource. And basically people have produced, through multiple resting state MRI scans from multiple healthy volunteers, maps of all of these resting state networks. And you can download it basically. And it's mapped to one of these standard neuroanatomical atlases. It's amazing work, kind of thing. And so we had a very bright medical student from Pavia who basically sifted through all this data, because it's quite noisy. You've got lots of disconnected components, so you need to sort of apply some thresholding to all of this, and then basically built for us in Slicer. Oh, I forgot to pull over the video, but anyway, you can see this. For those of you that use Slicer 3D, you'll recognize the UI. So she basically built us segmentations for these key networks, so we can propagate that onto the scan of an individual patient with a brain tumor. And then again, this is just a reminder of how these different networks sort of focus on some of these things that I mentioned that our patients really suffer with. Okay, so in Hamlet RT, what we did is to collect these questionnaire, and it wasn't just a neurocognitive assessment, because patients hate doing those. Well, can you sit there in clinic room for 45 minutes being asked to draw elephants? Or they really don't like that. So this is a bit more kind of focused. It actually talks about how does people's memory and cognition, tiredness and mood affect them on a day-to-day basis. And it actually came, CCSE stands for Children's Cancer Survival. And it's actually from people that had brain radiotherapy in childhood and then followed them as adults and said, what problems did you have when you returned to the world of work? And it's a very highly validated, very short instrument. And it, you know, a lot of bang per buck in terms of a short set of questions telling an awful lot about patients, you know, ability, their neurocognition in the place of work. Okay, so I then had this daft idea that what we could do basically is we could identify the grey matter areas that make up these attention nodes. So Mathilde's atlas basically does that for us, and we can propagate that onto an individual scan using some deformable image registration code that we've got. We then calculate the white matter connections between each node. And in order to do that, normally you would need diffusion tensor imaging to actually work out for each patient how those bits of each node connected. Because remember, sometimes they'll be thrown out because they've had surgery as well, not because of our radiotherapy. We then collect the dose statistics for each of those attention networks and then correlate them with the functional outcomes. So here's the rub. Resting state MRI takes over an hour for a patient, for a healthy volunteer in a 70 scanner. And DTI takes 40 minutes to get a really good, for tractography, basically, a really good DTI image. Brain tumor patients can't manage that. We're limited in our NHS brain tumor patients to about a 25, 30-minute scanning time for a standard clinical, you know, real world data set. If they're in a study, of course, they do get them. Okay. So what we did basically was to propagate those nodes onto the DTI map using deformable image registration. And then the idea is that we then use the DTI map to basically calculate the tracts between each of those nodes, so we could collect dose information out over it. So the fiber pathways effectively. And that's what you would normally do with DTI. So all we needed to do this, we didn't need the kind of high-level connectomic atlas that you need to study the disease of connections of the brain. So for example, if you're interested in Alzheimer's, dementia, or multiple sclerosis, you're really interested in like the microanatomical changes and how connections fail in the brain with those diseases. We just needed a broad brush map of connections so we could connect these broad areas of the brain, looking at it at the level of a radiotherapy planning scan. Come on, why aren't you going? There we go. So we used something called a cycle GAN to do this. And this is a particular type of generative adversarial network. And this is the where I'm faking it comes in, basically. So if you imagine a cycle GAN is sort of like two models back to back, facing each other, going in opposite directions. The first model ingests an MRI scan, and then it has a generator that tries to learn to produce a synthetic DTI scan from that MRI scan. And it then has a differentiator that tries to learn whether that whether that scan is either a real one or a fake one. And then under one kind of optimization function, so one goal, you basically want that part of the network to get as good as possible at generating fake DTI scans and being able to tell the difference between real ones and fake ones. And then back to back, you've got another one that goes in the opposite direction, basically, that starts with a DTI scan and generates a synthetic MRI scan and gets as good as possible at doing that and working out which is real and which is fake. I never understood why you needed the backwards layer, but it's the fact that this can go round and round iteratively. And then you might be able to understand that in a zero-sum game, both of these get as good as possible, and it actually enhances the performance of both the forward and the backward layers. Although clearly in our domain, we're only actually interested in the performance of the forward one, i.e. creating synthetic DTI from normal radiotherapy planning T1 weighted MRI scans. So this is unpublished data, so please don't share this, but this is the results of our cycle GAN using 1,000 patients, basically split across 850 to train and 150 to test. So this is the ground truth T1 weighted scan. I'm sorry, but the anatomical convention in our data loader has the head facing downwards, which is just a bit confusing. But this is the ground truth DTI connection map, what's called a fractional anisotropy map. That's the synthetic one, and that's the difference map. So you can see basically that for the purposes of just mapping out the connections between key areas of the brain on a radiotherapy scan, this is good enough. We don't, it's clearly not going to be completely accurate in areas of white matter disease, but it's good enough to build these things. So we have some algorithms that can do this tractography part work basically in 3 dimensions. But they are very, very computationally intensive if you're working with just the raw fractional anisotropy data, okay? There is a way basically of encoding this data so that you encode the direction of the white matter fiber using color. And so basically you can see this is called a directionally encoded color FA map. And what this shows is it shows the same white matter fiber connections in the brain, but green means from front to back, red means from side to side. So those of you that remember, this is the corpus callosum, the huge bridge of white matter connections joining the 2 hemispheres together. And blue basically means sort of in and out of plane, basically, rostrocaudal. So here you can see the fibers forming of the internal capsule. So taking all of those motor connections down into the spinal cord, about 1 million fibers in there. And so here you can see the sort of color convention by which we code that. So I realized that if we could generate synthetic color encoded map, we could use a much, much simpler agent-based computing approach in order to work out basically the path between any 2 areas of the brain. So for example, you could even use it, let's say you had a multifocal tumor and it had gone from here to here, you could actually get the algorithm to calculate the likely tracked path that connected those 2 areas of disease, you see. And this is just sort of hot off the press. So this is Doris's latest work, basically. And so here now we've got the ground truth MRI. These are the calculated directionally encoded color connection maps, the real ones, and then these are the fake ones. And then because of the color, we're showing the data in 2 planes, basically, because now you can see the fibers of the internal capsule. And again, it is just remarkable, basically, how well the algorithm can perform with enough data, but we needed to train on about 1,000 patients. So And so basically, this is the idea of how it would all fit together in this kind of giant oncosimulator. So we have the patient's anatomical images, and we would generate synthetic connection maps. Okay. In the end, we want to actually produce a machine learning model that's good enough at segmenting the actual grey matter nodes of the attention network, so we don't have to propagate an atlas onto each patient. That would be the idea. Then we generate the directionally encoded color maps, and we then calculate the connections between all of these areas. And then basically we have the radiation dose, and we have data from the patients as to how they responded to radiotherapy. So we can use that basically to try and make predictions that we can validate after radiotherapy treatment. And that's kind of the fundamental concept of what we're trying to do. And ultimately, what does this matter? Well, it matters in two ways. The first is that, unfortunately, we don't have enough neuropsychologists to see all of our brain tumor patients. So we have to cherry pick which ones we send, and we tend to send the younger, fitter ones, particularly those who are working. So if we had a tool like this that could perhaps make a baseline prediction that this particular patient, because of the configuration of where the radiation dose has to go, because you need to treat the tumor first, otherwise the patient's not alive to get neurocognitive problems. But it's likely that this configuration is going to cause specific neurocognitive problems of these domains. Then we could feed that forward into a much more targeted referral into a neuropsychologist early. And the neuropsychologist is more likely to say yes, if it isn't, oh, we're sending you every patient, but to say, well, look, we have some good, priors to suggest this patient would be really useful, benefit from early neuropsychology input. The second thing is that in general, with advances in our knowledge and radiotherapy delivery by epochs, the margins that we're having to put around tumors is getting smaller. And that's quite nice, because it then means potentially that as we find that it is safer to reduce margins around gliomas, we might actually be able to not just reduce, but actually kind of customize margins, particularly away from key parts of these networks. So we might make a trade-off and say, do you know what, actually, I'm going to pull in off here because my advanced imaging shows me there's probably not tumor in that area. And so it would really help basically to try and protect that particular area. Because often the problem we have with conformal avoidance in radiotherapy in neuro-oncology is, yes, we can do it. I mean, stereotactic radiosurgery shows we can be incredibly precise the way we deliver dose. We just don't know which part of the adjacent brain to avoid. So if we can have some kind of an educated approach towards that, then that would be really good. Okay, and so basically it's really nice. We've applied for a little bit of money to kind of take this forward over the next few years. And what's really nice is that it turns out there's a group at Aarhus University Hospital. They sent over one of their PhD students to come and work with our group because she wanted to learn more about transformer models and cycle GANs. And basically they've already collected a data set of patients, because in Denmark, any brain tumor patient, you can refer to their national center for proton beam radiotherapy instead of X-ray based radiotherapy if you have some convincing data to suggest that the dosimetry will make a difference to that particular patient, which is really nice. So they get referrals from all around the country, basically, for people where they're saying, look, we'd like to cut a bit here, shave a bit here, basically off where the radiation goes, and do that potentially using protons, because protons have a sort of sharper drop off to where the radiation goes. So we're particularly excited about kind of partnering with them, and that they would cross-validate our model with their data. Again, don't get me started on this, but basically I really feel, if you don't design cross-validation into building a clinical sort of evaluation of machine learning model, then you need to go back to the scratch and think about how you're going to do things, really. So, okay, so I'll finish there and open for questions, but hopefully it was a bit of a sort of quick sort of stream of consciousness thinking of sort of what we're trying to do. But I hope you find it interesting. There's loads of people to thank, and there's probably more that I haven't remembered. So thank you.
Thank you, Dr. Jena. That was really, really fascinating. And for someone that doesn't do machine learning, I think I learned a lot from that. And it was really interesting how you were able to incorporate clinical practice of it and the implementation. And the bonus was the colourful scans. So, so I'm just going to open up to questions. So feel free to ask, turn on your cameras or put your hand up or put the question in the chat. Otherwise, I know Matt will be asking a question. And
yeah, I mean, I'm keen for other people to ask questions, but otherwise, I'll just pester Raj for the next 25 minutes. So, I mean, Raj, I think it's really interesting. So if we just go back to some basics, how did you get Hamlet RT funded?
So we had some money from Cancer Research UK. They created so first of all, we got funded to do the initial feasibility for an AI study from Microsoft Research. We started off doing this in partnership with Microsoft. They then kind of moved away from this area, and then we'd set it up as a single center study. And then with the CR UK's RadNet fund, there was a fund that you could put in for collaboration projects. And amazingly, ours was the first to go into that particular thing. And so they agreed basically to fund us the extra money in order to take our platform and expand it to work in multiple centers. But because it's all digital and because the patient-reported outcomes are filled in directly by the patients, it's very cheap, so it wasn't an expensive thing to do.
Yeah.
Can I ask a question off the basis of that? How did you decide on the CCSS and CQ test as opposed to any other? Because you said that neurocognitive questions were difficult, but the fact that you came up with doing this one, what was the collaboration?
Again, it's really nice because this is, it's all team science, right? And as we expanded the network out, we get to speak to people like Florian Beale in Leeds. She's done a lot of work with the ORTC on neurocognitive assessments, and she had a PROM-based assessment, but she couldn't share with us at the time. But she said, she showed that it was possible to turn a neurocognitive assessment into a PROM. And then from that, I started looking at what was out there in the literature. And I realized I wasn't actually interested in the evaluations, right? Matt and I are interested in the consequences to these patients. And that's really when I came across CCSS and I thought, gosh, this is amazing. And also CCSS has been so well validated against a whole bunch of much longer neurocognitive questionnaires that involve sitting there and doing tests. And I thought, yes, I've found gold basically when I found that. So yeah.
Sorry, I'll let you get back to your question.
Yeah. And then just to go back, so I really like the idea of using synthetic DTI to bridge the fact that we don't have DTI. And as I think Mabuba's PhD, which is just about to start, is looking at something similar. And we can talk offline about some collaboration because we'll be collecting wearables data, which might fit kind of nicely into this. It measures something a bit different. But the DTIs that you're using, where are you getting them from to train the cycle GAN?
So this is a large public repository data set.
This is the Human Connectome project.
Yes, from HCP.
Right.
But what we've done is we've actually downgraded that because those are like enormous 70 images. So we've sort of downgraded those images so that they're more equivalent to the types of images that we get on a normal DTI scan.
So I guess my next question though is, although I'm sure you've shown some nice pictures and I'm sure you have metrics that show that the GANs produce nice synthetic DTI images, none of the HCP patients have brain tumours, I don't think. So do you know that your approach actually works in people who've also got a big lump in their head?
Indeed. And I think this is a key factor. I mean, and we've done a lot of work at looking at DTI in the infiltration zone. And the reason why this is valid to do is that in general, you can see that where you get infiltration, you get intact white matter tracts. And that correlates effectively with sort of, non-enhancing changes around tumors. Whereas where you actually get sort of the enhancing area of a tumor destroying a white matter tract, that's actually very apparent. So we're relying, basically piggybacking on that concept to say that effectively, if we're not seeing something as sort of enhancing disease in the tumor cavity or in the environment around it effectively, that we can still consider it as being a valid pathway basically that goes past that region.
Sure, but if you think about some people with large gliomas, you can clearly see distortion of the normal anatomy of the brain. So I assume that the underlying tracts will also be distorted, but your model's never seen a scan with a tumor in. So it's not
Indeed.
clear. It's not clear that the
Yeah.
synthetic tracts are really going to be accurate in that case, is it?
Yeah. So and that's what the 3 years of funding is to then the next step basically is we've got locally a reasonable cohort of patients, particularly colleague Stephen Price got the PRAM GBM study. So we actually try that and make sure that works as the next step. So,
Okay, no, I was just curious about that gap. Right. That's enough. Yeah, sorry, go on, Lily.
No, so you said you needed a large training set, which was around 1,000. So in the next head and neck one, are you going to do that with, again, do you need to have, as like Matt was saying, like the head and neck anatomical features, then the tumor one, and then how does that work if you're going to add a lump or different scans or different treatments? So are you going to do ones that go retrospectively at a treated brain or treated like head and neck cancer? Because would that affect or disrupt the tracks?
Yeah, so it's only good. This approach is only really valid in the brain tumor patients. First thing to say, and yes, we need to demonstrate effectively in a data set that the model can work in a patient that's actually had a resected brain tumor, and that's the key thing. The other thing that we've got in our data set is we have a baseline NCQ after surgery and before radiotherapy. So that's very, very helpful because, for example, if we already see very poor connections in a network before the patient even started radiotherapy, then that's a very good sign to say that actually surgery has already maybe disrupted this tract. And so it's the ability to, collect, and that's why you have to do these things and design them prospectively. So you can really map out, I really need this baseline, and then I need the ones after radiotherapy kind of thing, because then you can start to do things like that. So, yeah.
And would it make an impact difference on like the tumor? Because, for instance, if the glioma is more infiltrative than the meningioma, or let's say if it was an astrocytoma that was pilocytic first. So would that all does that all go into the models when you're doing it?
So the collection we're doing is only IDH mutated gliomas. So hopefully we're picking out a particular phenotype kind of thing. And interestingly, it may be that they're more infiltrative and don't proliferate as fast, but actually, in a way, that's even more interesting kind of thing, if we can build something that works on that data set kind of thing. Sadly, for glioblastoma, which is the bread and butter of what Matt and I do, most patients are not going to survive long enough to express these neurocognitive outcomes. Most patients are not going to return to work, sadly. So it's really, we're focusing on our younger patients who develop these IDH mutated tumors, which are excellent tumor treatment. They're going to live, a decade roughly or something like that. So, yeah.
Thank you. I see Andrew may have a question because he's moved. Yes, I can see that.
Thanks, Raj. So it sounds like your next bit of work is validating the cycle GAN in patients with brain tumor, because you've got a cohort, you've got DTI in, and then a follow-on piece of work from that is looking at building that predictive model in combination with a neurocognitive assessment to try and predict neurocognition later on. Are you doing some work in parallel to that? Because presumably you've got longitudinal scans on a large cohort of patients to use synthetic DTI to predict areas of progression. So the other side, not the toxicity side, but the sort of where is the tumor going to grow along? You've got the longitudinal data, and you've got the synthetic DTI.
I was in the post, Andrew. That was, of course, the hope with DTI. The hope with DTI was that if we can see the lacy fingers of the tumor spreading into the brain, we could predict where it's going. And I've been at this for a long time, and I find it's very, very hard. Stephen Price's study, PRAM GBM, is really trying to understand this, whether DTI can help you predict areas of recurrence, particularly in the area around where he's actually operated, kind of thing. But I just think that's fantastically difficult. And as a group, we've been at it for 20 years now. And the reason that DTI isn't standard of care is that if it was able to do that, we'd all be using it all the time, kind of thing. So, you know, I think there's certainly signal in DTI, you know, and I might be a DTI fanboy, I guess, you know, but I think that for tumor, it is just so much more difficult. And I think maybe combining it with functional imaging, maybe actually metabolic imaging, I think that's the thing I'm really interested in, is things like, you know, deuterium labeled glucose and things like that. And then if you see basically, if you consider the zone of a tumor as a clock face, and if you see increased metabolic activity on 1 hour of the clock face, and you see DTI abnormality in the direction there, maybe you could then take a punt and say, well, that's the direction the tumor is going. But I think with just DTI on its own, it's not enough to do that.
Just on that note, Andrew, Elsa and I had a master's student trying to do a temporal GAN. So given a scan at time point T0 and a training set where you have scans at time point T1, whether you could predict the scan that was going to come up in the future to try and predict progression. That didn't work.
Nightmare. Yes. Yeah,
It's a really nice idea, and the nice thing about it is it's entirely theory free. You just, you know, threw a bunch of data into a GAN and see what came out, but it certainly didn't work. It might be because we didn't have enough data. It's actually, when you look at it, it's actually surprisingly difficult to assemble longitudinal imaging data sets in glioma patients.
Do you think that it was a function of not enough data and a heterogeneous nature of it? You know, if you had enough scans that looked similar, you could predict ones near the corpus callosum are going to go through the splenium, kind of thing.
Yeah, I suspect so. And you know, because we were just doing it as a master's student, we took 150 patients that we had scans anonymized on. Yeah. And yeah, they were mostly GBM, but there would have been some grade 3 astros in there, some, you know, it was just, it was a slightly, and of course the scans were done at slightly different times because it was standard clinical follow-up and stuff moves around and things. So it might work if you did it with a lot more care and a lot more data, but it's clearly not trivial to do.
If anyone wants to have a go at a cycle GAN, have a look at Pix to Pix. It's a really, really good library, and it's yeah, it's very very impressive.
Just because we've got a minute, Raj, all of this data looks lovely. I would encourage you to think about archiving it in the Brain Tumor Data Accelerator.
Okay.
I mean, this is a brain tumor charity funded project.
Yes.
That provides a secure TRE. There is a small amount, but there is funding to pay for you know, data anonymization and upload, and it means that other people can make use of it, but it also means that you get access to a wider data set. So,
and I was going to say about like the ZGBM, how does it fit in with other imaging ones? Because I know that's a GBM one, but it's collecting information and data as well as the imaging from patients who have gone through treatment or are going through treatment with a glioma. So again, I didn't know how that integrated, because I know they are on standard MRIs, and does that make any difference if you don't have the DTI scans, and is it able to then predict on those scans? But I think for me, the other element of it was, I'm going to go back to the neurocognition and the POMS, that's a bit more of my interest. And then how does that get integrated into the model? So how do you envisage that next step of allowing for that integration to come in to feed into the automation? And because you said there's like true and false, and so you're faking it, but that is something that's a hard yes or no, because it's information that it's real and it's either factual or it's not. But then the only other thing is, how was that data collected as well, and is that data self-reported, and how has the drop-off been, and is it on a one-off time basis? Or
so it's 3-month intervals kind of thing. And I'm not allowed to see the data. So I'm not allowed access to the REDCap system until study completes recruitment. So that way I stay clean, basically, because I intend to be involved in the analysis of the data, of course. But I think the key thing is that this is a really good example of late data binding, all right? Because ultimately, you can take the CCSS questionnaire, which will end up with, let's say, 12 or 15 numbers, or you can even reduce those into the domains of the questionnaire kind of thing. And you will then have effectively some summary dose statistics for 6 brain networks. Okay, so like a dose volume histogram. So that is a tractable amount of information. And my principle always is, if you could start this analysis with something like linear regression that you really understand, and you think, all right, I could give that a go, that's a good point to then say, okay, let it rip with a machine learning algorithm. Because I really hate it when people pull together these 1,000 parameter data sets and put it straight into an integrative model. You've got no baseline to compare it with. So if you can get it simple enough where you can say, well, let me just try with regression, and there's some signal there, that makes it so much easier for you to then look at the machine learning model and see what it's doing and whether it looks as if it's doing something believable or interesting kind of thing. So that's what I'm a really, fervent believer that you do late fusion of your data. We are medics, we understand relationships in our data as well. We can encode some of that when we simplify data, sort of thing. And this approach is just shoving it all into a big model. It's no good. And exactly as you say, how would you integrate that into the layers of the cycle GAN? I've absolutely no idea how you do that. So
yeah, I think your point about linear regression is well made, and every time we have computer science students who want to build a model, I insist they build a regression model first.
Yeah.
You then get very disappointed when whichever technology they're interested in that year doesn't outperform a regression model.
Exactly. Yeah.
Because if you don't build the regression model, you can assume that your new model works really well. But if you make them build a regression model first and turns out that nothing beats the regression model, you get bounced.
Yeah.
Cool. Any other questions?
Yeah, I've got a question if you can hear me. Hi,
Yeah.
Thanks for the presentation. I'm Ulrich, I'm a patient. And the question is, did you or some other teams consider applying a similar technique to different treatments, so namely chemotherapy, for example, or a combination of chemo with radiation? Yeah, that's the question.
No,
and if they did, what was the outcome?
Yeah, no, that's a really good point, Ulrich. I mean, there's clearly some kind of effect of chemo brain sort of thing in patients receiving chemotherapy. But I think the approach to this ultimately relies on the fact that, as I said at the beginning, radiotherapy is a spatially directed treatment. We can decide to some extent where we want to put it and where we don't want to put it. Whereas chemotherapy is going to affect the brain in a more global way. So it may be that you do not need such a spatially involved, shall we say, model if you're trying to correlate chemotherapy with brain cognition effects kind of thing, because we don't know,
perhaps
for example.
The counter argument is that the tumor is going to be where it is. I mean, obviously it's going to evolve and it might mutate and move and what have you. But the baseline is always going to be the tumor you got on the scan. And so that's what's kind of what I was expecting, is that by doing taking the approach you've been taking and applying it to chemo, perhaps you would see which type of tumor is more or less likely to be disturbed or cured by a particular molecule.
I think that's valid, and I think that, but I think it does come back to the interaction between the tumor and the host. And
right.
what you're describing with chemotherapy is probably better by modeling the tumor bit rather than the host bit. And I think this bit really relates to the host. So, but yeah, no, it's certainly an interesting idea. So yeah.
And on that note, we have another question on what are your thoughts on immunotherapy versus chemotherapy for cancer treatments? But that's not related to the cancer, right? Is that in relation to?
You mean just
I
in
didn't know if
general?
that was a follow. I didn't know if that was a follow on from Ulrich's question around if you were then to map it on. Okay.
Oh, just a general question, yeah.
Okay, I thought maybe they meant is it the same way that Ulrich was asking? Have you thought about using this model for like those that have chemoradiotherapy versus radiotherapy? But now, as we advance and more treatments are coming out, will that impact the way that you're?
Undoubtedly, treatments down the line might impact, but I think that really, as I said, we're interested in the radiation part of the perturbation to the brain, really, with this particular model kind of thing. I mean, I think, I'm very jealous of my colleagues that get to use immunotherapy in other parts of the body and see amazing results. Personally, I think, it's, to me, it just, we know brain tumors don't have the same effect in the immune system, just very briefly, but it just feels to me like it's a problem of sort of finding the needles in the haystack. If we could define and work out which patients, for whatever reason, the immune system might be able to then access the tumor, then maybe those are the ones that might benefit from immunotherapy. But our very crude studies of trying to give immunotherapy to all patients with a particular type of brain cancer have been not really very successful, which is a real shame. So yeah.
Can I ask the question on the DTI? So you know how these imaging have now been used to improve the surgical quality. Do you think there would be a function then to do this like mapping previously, so before the surgery, so to generate a stimulation of what it could do without putting the patient in the scanner if you haven't? Or does that make sense? What my question is trying to ask?
Yes, it does. I mean, but the surgeons do use DTI and tractography already when they're planning certain types of surgery. So they've already got some of these technologies, available, sort of thing. But it tends to be in the sort of younger, fitter patients too, sort of thing. So yeah.
Andrew, I can see you've turned your camera on. Do you have one more question? I've got time for one question.
Thank you. I just wondered if you could give us a bit of insight into some of the methodological ways you set this up, because presumably, from my recollection, at the beginning, it was a collaboration between industry, university, NHS. Obviously, computationally expensive to do the auto-segmentation work and so on, which can't be done on NHS servers where, within that, you've got industry involved as well. What were the regulatory data storage? Was there complexity in that? How did that get set up and so on?
It's a very interesting point. So Microsoft wanted basically to be able to access a system whereby the data collected in the study, they could send models to be run against it with the cloud system in our hospital that happens to be a Microsoft one. We have a small cloud area that we can use for research applications. As it happened over time, their interest in that reduced because they sort of open sourced that particular bit of tooling kind of thing. But what it left us with was that we had a sort of research cloud that we can use to collect all of the data. And we created a governance model that said that we could allow to send particular data sets between the hospital and the cloud, always through a consent model, basically. And that was really the key enabler, because as you say, you can't run this kind of computing on a hospital computer. So we had to have a way of getting it out into the cloud and then running these models from there.
Thank you so much for all the talk and all the answering all our questions, because I know we've had lots of questions to ask. And I have put a link to a Qualtrics survey in the chat. So if everyone can do that, that would be great. And the next speaker will be Mr. Jenkins